Okay, here's the second lecture. From the lecture number one, we talked about relativity as a coordinate symmetry. It means the physics equation are unchanged under coordinate transformations. Now, the Galilean transformation involve only space, x prime. Lorentz and Poincaré worked with space and time quotation mark, because they don't really believe the time uh, as physical, but Poincaré later on realized that the time could be real. And but anyway, the key point is Einstein arrived at the same Lorentz transformation using a new conception of time, which means a new kinematics. So in this uh, chapter two, we're going to talk about the new kinematics of special relativity. In particular, we're going to talk about how the Einstein two postulate leads immediately to Lorentz transformation. So we'll give Einstein's derivation Lorentz transformation. The new conception of time. Uh, Einstein's sixth sense led me uh, to a strong belief that the principle of relativity should be valid. And also, he strongly believes Maxwell's electromagnetism as a basic equation in physics. But these two ideas, of course, relativity at the time, of course, people thinking of Galilean transformation and the Galilean velocity addition rule, U prime U minus V. Yet Maxwell's equation lead to C prime equal to C. The speed of light is unchanged. This seems a clear contradiction. Okay, and Einstein worried about this for a long time. He struggled later on. People asked how long he'd been thinking this problem. He said about 10 years when he was 16 until 26, 1905, when he was 26, finally came up with the resolution. And what came about, what triggered is 1905, Einstein had a long discussion with Mikhail Bessel, his classmates from ETH and his patent office colleagues, and a real lifelong friend. In fact, the only person he acknowledged in his paper was Bessel. Anyway, the discussion led to his epiphany that the classical absolute time, that t prime equal to t, has no experimental foundation. There's no experiment to say that t is equal to t prime. And in this connection, he was also influenced by the so-called the positivistic philosophy of David Hume and Ernest Mach, who advocated that we should discard abstract concepts if not connected with observable effects. Okay. And so absolute time, ether, they have no experimental effects, observable effects, so we shouldn't use them. And the definition of time, according to Einstein, ultimately is related to the notion of simultaneity. Two events happen at the same time. In the next slide, we show that if signal transmission is not instantaneous and we see it's not infinite, the simultaneity is relative. Meaning that if we had two events where simultaneous to one observer, it can be not simultaneous to another observer in another coordinate frame. So therefore, time, just like space, is observer dependent. Depending on which frame you use it to use a different observer. And the fact that the time is coordinate dependent, you will see immediately leads to Lorentz transformation. So now we're going to talk about relativity simultaneity. Before we talk about this new idea of simultaneity can be relative, let me recall something which we all know, familiar with. It's the spatial version of the relative simultaneity, which is relative equilocality. And it was if two events happen at the same place in one reference, they can be viewed as happening at two separate places by another observer, moving by a moving observer. So let's consider a concrete example. Let's say that an observer is in a moving rail car. So in the to him the car is not moving, but then and the rail car, let's say at certain time, a pulse was sends out. Okay, a little time later, and another pulse sends out. To him, this emission of the two light pulses are happening in the same place, so therefore they are equilocal to an observer on the rail car. Okay, so therefore they are equal. But to an observer on the rail platform who sees the rail car rushing by, these two events obviously happen not the same location, so therefore delta x is not equal to 0. And this is easy to even the Galilean level. You have x dx prime equal to dx minus vtt. So therefore, even the x prime equal to 0, if the size 0, I still can have delta x, in fact, not equal to 0 because that's equal to v delta t. And of course, Einstein was new. Einstein is introduced the spatial, the temporal version of this phenomena. So you have relative simultaneity. If the two events are simultaneous in one frame, they can be viewed as not simultaneous by another observer. So let's look at this relative simultaneity again using rare cars. This time now the emission of the two pulses is took place at the midpoint of the rear car. So two light poles back to back is emitted. Okay. What's simultaneous is the two light poles reaching the ends of the rear car. These two events, because it was emitted at midpoint, they arrive at the same time to the observer on the rear car. Okay, so T1 prime, T2 prime are the same. So that's simultaneous to the observer on the rear car. And that's I call O prime frame. But now to an observer on the platform with the car rushing by. Okay. Now, even though the light pulse emitted at midpoint, because the back of the car has moved closer, so the distance the light has to travel to reach the back end of the rear car is takes less time. So T1 is smaller than T2. The time takes the light pulse to reach the front end of the rear car, which had moved away from the midpoint. Okay. So in this case, T1 is less than T2, so no longer simultaneous. So this is in the observer on the rear car, they're simultaneous. To the observer outside the rear car, the stand on platform, you will see two events are not simultaneous. Now you notice we use the light signal to decide whether they are simultaneous or not. And the reason is because light has the unique property, it travels with the same speed, no matter the source or receiver of the light are moving or not. Because whatever it is, they always move with c. So therefore, if the distance is shorter, because the same speed, we should take a shorter time. Distance longer to travel, it to take a longer time. Suppose now, consider a related instance. Suppose instead of the light source emitted from midpoint, but it is, let's say it's closer to the front end. So therefore, even for the rear car, okay, observer, it would take a longer time for the light pulse to reach the rear end than the front end. So therefore, T1 prime is greater than T2 prime. Still, you can imagine, if the rear car moves fast enough, it is possible for T1 prime to less than T2. So therefore, the order events can be relative. In one case, uh, uh, the T2, the front end event is prior to the second to rear end events, and yet in the to a platform observer, they have different orders. So we have the relativity event order. Okay, later on we see it's also interesting implications. So we have relativity of of simultaneity, so T prime doesn't have equal to T. Once you have that possibility, then it is possible C prime equals C. That's what we really see, because the relation between inertial frame are no longer by Galilean. So the Galilean velocity rule doesn't have to be valid. In fact, be changed uh, by Lorentz transformations, and that would be possible. So therefore, Einstein was able to put down two postulates of special relativity. Besides, of course, the principle of relativity, saying all physics are all the same in all inertial frame. But also, he viewed Maxwell's equation is also to be valid in all inertial. So therefore, the constant speed is the basic law of nature, and he simply took that to be the a basic postulate. You have the same c in all inertial frames. You will see these two postulates directly leads to Lorentz transformation, and in fact that's what leads to all special relativity effects. Now, before we do any formalism, derive Lorentz transformation, etc., let me first we can already derive the famous equal to mc squared result from these two postulates. Okay, so we'll first look at this. Now, this equal to mc squared was actually arrived to Einstein after he sent out his paper on special relativity. So his second paper, 1905, basically like an addendum to say he can show equal to mc squared. Now, that paper actually is somewhat complicated, because in order to derive these results, you need to know the Lorentz transformation of the electromagnetic field, how the radiation viewed by relative observers will be different, and how the volume can be different. Altogether, you can show equal to mc squared. But some 40 years later, he had to give a popular talk at, I believe, in Israel. Then he realized that this can be derived much simpler without all those complicated transformations, just directly from the two postulates. So this is the version we're going to use in our derivation. So this is actually in chapter 2, the box 2.1, the 1946 derivation by Einstein of equal to mc squared. Let's consider an atom radiating a back-to-back light pulse. Okay, so before I have this atom, then after I have the atom, may have a different mass. We allow the possibility of different mass, and it has radiate. So by energy conservation, then we know the change energy of an atom equal to the photon energy back to back. So each carries E gamma, so there are two of them, so 2 E gamma. Now we're going to apply principle of relativity. We can say how this event of radiating two light pulses by an atom can be viewed by two different observers in relative motion. The first observer is the first picture, A, is at rest with respect to the atom. So the light pulse going up and down. The second observer is moving to the left. So therefore, to that observer, the atom is moving to the right, and with origin velocity v. And the light pulse emitted now would have an oblique angle theta. Okay, it should be the same physics, but as viewed by two different measures slightly differently, but it should be the same physics. Now, the key point is that these are light pulses, so lights. So therefore, they travel velocity c, even if it has x component in the v. Even this light moving this way, its speed is still c. So the length of this diagonal still c. So therefore, the cosine of this angle in this, look at this rectangle triangle, the horizontal length is v, the diagonal has c, so therefore cosine theta is simply equal to v over c. So therefore the photon momentum has an x component, is simply the magnitude of the momentum p sub gamma times cosine theta, which you say is V over C. So therefore, P gamma V over C. And then the momentum conservation relation says, in particular along the x direction, is that originally I have big M times V. That's original. After emission, it may allow a small different M, so I have MV still. But then you have to add the photon momentum along the x direction. So each is P gamma V over C. That two of them. Okay. So now each term has a V, so I can cancel the V. So I have big M equal to initial mass equal to the final mass times 2P gamma over C. Now, the photon energy and photon momentum are related, okay, by this relation. But E gamma equal to PC over C. You say, well, this is a relativity relation. We are just starting talking. We haven't derived anything. No, you don't need to derive. You don't need to use view as, I mean, to say you need to know this relativity is. In fact, in classical physics, we already have relation between the energy density and momentum density. Remember the Poynting vector, and you have this relation. So using the relation, okay, we can basically substitute. We substitute here, so this is equal to uh, uh, 2e gamma over c squared. Then replacing e gamma by the change in atomic energy. So therefore, the change in atomic energy is equal to big MC squared minus small m c squared. So this is the result, which says the atom energy has a constant term. We call it the rest energy of the particle, which is equal to E equal to mc squared, whether it's initial or final mass. So the difference is that, so this is just a form of energy, and because we know it's energy, because it can convert into other form of energy. In this example, convert it into radiation energy. Okay. Now we're ready to derive the full special relativity formulas and basic starting with derivation of Lorentz transformation. So this and the first segment of the second lecture.